Have you ever looked at a simple flower and felt that you were only seeing half the story? I have a friend who is an artist, and he often expresses a viewpoint that I find myself disagreeing with on a fundamental level. He will pick up a delicate blossom, show it to me, and say, "Look at how magnificent this is." And I will certainly agree with him. But then he takes it a step further. He says, "As an artist, I can truly appreciate the aesthetic beauty of this flower, but you as a scientist want to dismantle it. You want to take it all apart, and when you do, it becomes a dull, mechanical thing." I honestly think that perspective is a bit nutty. When I gaze at that flower, or even a simple glass of clear water, or the rhythmic ticking of a clock hanging on the wall, I am not just observing the surface-level appearance. I am seeing the inner machinery. I am seeing the breathtaking complexity of how it all functions. When you take the time to look at the machinery of the entire universe, and specifically the machinery of time itself, you discover that nature is operating in a manner that is completely absurd. It is absolutely, wonderfully ridiculous. As human beings, we all share this deep-seated intuition, don't we? We feel in our bones that time is like a relentless river flowing in one single direction. If you drop a ceramic teacup, it shatters into 100 pieces on the floor. You never see those sharp shards suddenly jump back up and reassemble themselves into a perfect cup. We grow older. We never grow younger. The past is finished and written. The future is a complete unknown, and we are forever pinned in this razor-thin, fleeting moment we call the present. We are always moving forward, never back. But what if I were to tell you that this entire picture, this arrow of time that feels so solid and undeniable to your senses, is actually nothing more than a statistical accident? What if I told you that at the most fundamental level of reality, down in the subatomic realm where electrons and photons play their strange games, there is absolutely no distinction between the past and the future? In fact, the truth is even crazier than that. To solve some of the most significant problems in modern physics and to make the complex equations actually work, I had to introduce a concept that sounds like pure science fiction, yet it is documented science fact. I had to work under the assumption that particles can, and frequently do, travel backward in time. Whispers. That is right. The very electron residing in your fingernail at this exact moment might be the identical electron that was floating in your coffee 10 minutes ago, simply traveling back from the future to visit you once again. It sounds like madness. It sounds impossible. But nature does not care one bit about what we humans think is impossible. Nature just exists. Today I want to take you on a journey through the bizarre behavior of time and explain how a paradox regarding looking backward actually helped me earn a Nobel Prize. We are going to dismantle the clock of the universe together, and we might find that we cannot put it back together in quite the same way. If you find yourself captivated by the hidden gears of reality and want to dive deeper into the mysteries of the quantum world, make sure to join our community now. Hit that subscribe button on Feynman Analysis to ensure you never miss an exploration into the unknown. Now, before we dive headfirst into the nitty-gritty details of electrons moving the wrong way through history, we need to address why any of this actually matters. Why should you, an average person, care if an electron is moving backward? You have monthly bills to pay. You have a family dinner to cook tonight. Why does the field of quantum electrodynamics matter to your daily life? Well, it matters because you are made entirely of this stuff. You are essentially a massive pile of atoms. And if the fundamental rules that govern those atoms allow for time to flow in both directions simultaneously, then our entire concept of reality, of what it truly means to exist in a specific moment is built on a fundamentally shaky foundation. Most people spend their entire lives thinking the world is a stage and time is the rigid script that tells the actors exactly where to go next. But in the world of physics, we have discovered that the script is written in a language that reads exactly the same, whether you read it forward or backward. If you do not grasp this concept, you are missing out on half the beauty of the entire universe. You are seeing the outward petals of the flower, but you are missing the profound wonder of the microscopic photosynthesis happening inside. So I have a proposition for you. This isn't just another dry physics lecture. This is an official invitation to stop looking at the world with your everyday habitual eyes and start looking at it through a more analytical scientific lens. We are going to try to turn your intuition completely inside out. If you enjoy the sensation of having your mind slightly bent, and if you want to join us in this honest, difficult, and wonderful pursuit of finding things out, then I want you to stick around. Science is a journey of constant discovery, and your curiosity is the engine. If you're ready to challenge everything you think you know about the physical world, click the like button and subscribe to Feynman Analysis. Let's find things out together. Let's begin with something that seems simple, or at least something that appears simple on the surface: light. Curious, when you look into a mirror in the morning, you see your own face. Light travels from your face to the mirror, bounces off the surface, and returns to your eye. It seems easy, right? The light travels in a perfectly straight line, hits the glass, and comes right back. That is what we are taught in school. That is what the ancient Greeks believed. But let's look closer at the machinery. Let's ask a deeper question. How does the light actually know where to go? Imagine for a moment that you are a lifeguard stationed on a sunny beach. You are sitting in your high chair, and suddenly you spot a swimmer struggling and drowning in the water. You need to reach them as fast as humanly possible. Now you can run very fast on the firm sand, but you swim much slower once you hit the water. If you draw a perfectly straight line from your chair to the swimmer, that is technically the shortest distance, sure. But is it the fastest path in terms of time? No, because that straight line forces you to spend too much time in the water where your speed is significantly reduced. So, what do? You run a little further down the beach, staying on the sand longer to maximize your high-speed travel, and then you angle into the water at a specific point so you have a shorter distance to swim. There's one specific path, a bent path, that takes the absolute minimum amount of total time. Surprised? It turns out that light does exactly the same thing. When light travels from air into water, it bends, it refracts, it changes its direction. Why does it do this? To our eyes, it looks as though the light calculated the path of least time. It looks like the light sniffed out every single possible path and said, aha, that specific one is the fastest. I'll take that one. This is known as the principle of least action. And for a very long time, this concept bothered me immensely. Think about it. A photon is just a tiny, dumb particle. It has no brain. It has no built-in calculator. It doesn't possess a map of the beach. So how does it know which path is the fastest before it even arrives? Does it smell the destination? Does it send out little scout particles to report back? Hey guys, check path A, then check path B, and let me know which one is quicker. No, that would be creating a complicated mechanism that simply doesn't exist. We are trying to impose our human logic, our logic of making a conscious choice, onto a mindless particle. The answer I eventually found, and this is the very heart of what we call the path integral formulation, is Much more bizarre. The electron or the photon does not choose the best path. Instead, it takes all of the paths, and I mean that literally. It takes every single possible path. Imagine a particle trying to get from point A to point B. It takes the straight path. It takes the curved path. It takes a path that goes to the moon and back. It travels to the very edge of the universe and returns. It goes backward in time. It performs a massive loop-de-loop and then heads forward again. Surprised? It sounds absolutely crazy to claim that it takes all paths simultaneously. You might ask me, Richard, surely the particle has to be in one specific place at one specific time. And I would tell you, no. That is the old way of thinking. That is the classical way of viewing the world. In the realm of quantum mechanics, we have to sum over the histories. We have to add up every single possible way the event could have occurred. Each individual path contributes a tiny arrow, which we call an amplitude, to the final answer. Think of it like a stopwatch. Imagine a tiny stopwatch attached to the particle itself. As the particle moves along a certain path, the hand of that stopwatch turns. Round and round it goes. The speed at which it turns depends on the energy involved. Now, for a truly crazy path, like going all the way to the moon and back, the time it takes is vastly different from a slightly less crazy path. Therefore, the stopwatch hands for those wild paths end up pointing in all different random directions. One points up, one points down, one points left. When you add 1,000,000 arrows pointing in completely random directions, what do you get? You get zero. They cancel each other out. The crazy, improbable paths essentially destroy each other through interference. But for the paths that are right near that perfect path, the path of least time, the times are all very similar. This means the stopwatch hands are all pointing in roughly the same direction. They don't cancel out. Instead, they add up. They reinforce each other. So the reason light looks like it travels in a straight line, and the reason the lifeguard looks like he chose the best path, is simply because all the other infinite paths cancel themselves out. The miracle of the straight line is just an illusion created by the interference of infinite crazy histories. Now, this is where the story gets really interesting. This is where we have to talk about the nature of time itself, because one of those crazy paths I mentioned earlier involves going backward in time. When I was working on quantum electrodynamics, or QED, which many call the jewel of physics, I ran into a massive problem. We were trying to calculate exactly what happens when two electrons scatter off each other. You have one electron coming in, another electron coming in, they exchange a photon, smash, and they go flying off in different directions. But the mathematics involved was an absolute mess. We kept getting results that were infinities. We would try to calculate the energy of the electron, and the answer would come out as infinity. You cannot weigh infinity pounds. Chuckles. We had to find a way to organize these chaotic events. So I started drawing little pictures. Today the world calls them Feynman diagrams, but to me they were just a practical way to keep track of the chaos. In these diagrams, time flows from the bottom of the page to the top. Space is represented from side to side. So a straight vertical line going up represents a particle sitting perfectly still in space while moving through time. A slanted line represents a particle moving through both space and time. Now look at this. Suppose I have an electron moving along, and suddenly, at a certain moment, it emits a photon and changes its direction. Okay, that's simple enough. But what if I draw a line that zigs and zags? What if the line turns around and points back down toward the bottom of the page? If time is supposed to be going up, what does a line going down actually mean? It means the particle is moving backward in time. If you were watching this event like a movie, what would you actually see? You would see the normal electron moving up through time, but then, seemingly out of nowhere, at some point in the future, a pair of particles appears from nothing. One is a normal electron, and the other is, well, it looks like an electron, but it has the opposite charge. It is a positron, an anti-electron. So now for a brief moment, you have three particles, the original electron, the new electron, and the new positron. Then the original electron meets the positron. They crash into each other. Poof, they annihilate. They disappear in a bright flash of light, and you are left with just the single new electron moving forward. This is what the event looks like if you slice time moment by moment. It looks like the spontaneous creation and annihilation of matter. Excited, it looks like magic. But if you look at my diagram, that zigzagging line, it is actually just one continuous path. It is just one single electron. It went forward in time, turned around and went backward in time, appearing to us as a positron, and then turned around yet again to go forward. This was the great revelation. Antimatter, the positron, is essentially just an electron moving backward in time. Now you have to be careful here. I am not suggesting you can jump into a time machine and go back to change history. I am talking about the fundamental symmetry of the equations. In the math of the Dirac equation, there are solutions for negative energy. People used to be terrified of them. They tried to hide them or explain them away. Dirac even tried to imagine the entire universe was filled with an invisible sea of electrons to account for them. But I thought that was far too complicated. Nature is fundamentally simple. If you take an electron and you reverse the flow of time, changing tau to tau, it looks exactly mathematically identical to a positron moving forward in time. To the universe, past and future are just directions, much like left and right. Think about slicing a sausage. Imagine that the whole of space-time is one giant cosmic sausage. The length of the sausage represents time, and the width represents space. Now, you and I are slicing that sausage at a 90-degree angle. Each slice is what we call now. Each slice is a moment. We see the circle of meat, and we call it the present. But imagine someone moving incredibly fast, perhaps someone on a spaceship. Relativity tells us that their now is tilted. They are slicing the sausage at a completely different angle. What I perceive as the past, they might see as the present. What I think is the future might already be contained in their slice. The events, the atoms, the collisions, and the history are all already there in the sausage, the block of space-time. We are just crawling through it, discovering it slice by slice. But the electron doesn't just crawl. The electron can loop back on itself. This leads to a thought that I once discussed with my advisor, John Wheeler. It is a thought so massive that it might make you feel dizzy. We know for a fact that all electrons are identical, exactly identical. You cannot tell one from another. They have the same mass, the same charge, and the same spin. Every electron in your brain is exactly the same as an electron in a star a billion light years away. Why is that? Why is nature so incredibly repetitive? Why didn't she make some electrons a little fatter, or perhaps a little bluer? Wheeler called me up one day and said, "Feynman, I know why all electrons have the same charge and the same mass." "Why?" I asked, surprised. "Because they are all the same electron. Imagine the zigzag I told you about. Forward, backward, forward, backward. Now imagine that this one single electron zigzags back and forth through time enough times to cover the entire universe. When it moves forward, it appears as an electron. When it moves backward, it appears as a positron. If you take a slice of now through this massive tangled mess of one single thread, You would see billions of points where the thread crosses the slice going up, and billions of points where it crosses going down. We would look at that and say, oh, look at all these trillions of distinct particles. But in reality, it could be just one single particle weaving the entire fabric of reality by exploring every possible moment in history. The universe is far stranger than we can imagine, but that's what makes it so beautiful. If you want to keep exploring these mind-bending concepts and see the world through a new lens, share this video and subscribe to Feynman Analysis. Your support helps us keep the pursuit of knowledge alive. Now, we didn't quite make that specific "the" story work perfectly. There aren't enough positrons in the observable universe to match the number of electrons, but the idea itself captures the true spirit of what I am trying to tell you. Whispers. The separation between past and future is a stubborn, persistent illusion. In the equations that govern the lights in this room, the atoms in your physical body, and the burning of the sun, the arrow of time simply does not exist. The machinery works both ways. We are accustomed to thinking of the world in terms of things happening, no cause and then effect. You push the swing and then it moves. You strike the match and then it burns. But that is just the macroscopic view. That is just the statistical average of billions of atoms crashing into each other. Down deep, underneath it all, there is just a dance. There is a scattering, particles interacting, exchanging information, and exploring paths. They don't know which way is tomorrow and which way is yesterday. They simply sum over the histories. They explore the possibilities. And out of that chaos, out of that infinite exploration of paths, arises the stable, solid world you see around you. The world where cups fall down and don't come back up. The stability of your daily reality is built on a foundation of absolute temporal chaos. So what does this mean for us? It means that the universe is far more interconnected than we ever dared to imagine. It means that history isn't a single line written in stone. It is a sum of infinite possibilities. We are still just scratching the surface. We have found the rules of the game. We know how the pieces move. We know that the bishop stays on its color. We know the electron can go backwards, but we don't know why the game is played. We don't know who set up the board in the first place, and that is okay. Excited. In fact, that is the best part of being a scientist. People often ask me if knowing the physics takes away the mystery, if knowing that the rainbow is just refracted light makes it less beautiful. I say no. It adds to the beauty. It adds the beauty of the mechanism. It adds the mystery of why the mechanism is so elegant. You are sitting there in the middle of this vast, confusing, wonderful universe. You are made of particles that might be traveling backward in time right at this very moment. You are a bundle of quantum amplitude summing up to a conscious being. That is a marvelous thing to be. We have so much more to find out. We have only just looked at the first few pages of the book. So if you want to keep reading this book with me, if you want to keep slicing the sausage and finding out what's inside, share this video with someone who thinks they know exactly what time is. Shake their world up a little bit. Nature is there waiting for us to figure her out, and she is far more imaginative than we are. I'll see you in the next one. Or maybe if the electrons are right, I've already seen you in the future. Would you like me to expand on the specific math of the path integral? Or explore another concept in quantum mechanics?